Hi, everyone, and welcome to this next installment in my algebra and pre-calculus video series. The topic of this video is something new, analytic trigonometry. All right, so in this video, we're not going to be evaluating trigonometric functions or graphing or solving equations. We're going to focus on verifying identities. And another word for verifying, didn't mean to go forward just yet. Another word for verifying is proving that a statement is true. Now, very often in mathematics, we're asked to take certain things with a bit of faith, take certain things for granted. You're given a formula and you're told that it works and you're told to use it, but you're not explained why it works. Okay, so for example, hopefully at this point, you've heard of the Pythagorean theorem. Now, if you have a right triangle, any right triangle, and we label the sides A, B, and C, and let's say you know two of those sides. Let's say A is equal to 5 and B is equal to 12. You should know how to find that third side. We have a formula for that. A squared plus B squared is always equal to C squared, where A, B, and C are the lengths of sides of a right triangle. C is the longest side, A and B are the other two sides. A squared plus B squared always equals C squared. So we could solve this, right? Plug in some numbers, 5 squared plus 12 squared is equal to C squared, and so on. We could solve from here, right? We're using this Pythagorean theorem, but have you ever wondered why this is always true? Why does A squared plus B squared always give you C squared? Where did that come from? Well, it turns out that proving a statement is sometimes much harder or more complicated or more difficult than actually using it. So proving the Pythagorean theorem, well, that's I'd say a few steps up in difficulty when compared to using the Pythagorean theorem. But that's what we're going to be doing today in this video, proving or verifying that certain statements are indeed true. Okay, so before we get into it, a little bit of a review. These are some of the identities that we've covered previously. And I'm calling this chapter 5, Analytic Trigonometry. In the previous chapter, we talked about an introduction to angles. Then we talked about the unit circle definitions of the 6 trig functions, and we talked about the right triangle definitions of the 6 trig functions, and so on. We talked about graphs. We talked about inverse trig functions. And these are some of the things we came across along the way. We've got what are called the reciprocal identities. There's really nothing to prove here because these are all a direct consequence of a definition, right? We defined the sine function, for example, as being equal to the y coordinate of the terminal point. We define the cosine, or the cosecant function as being the reciprocal of the y value of the terminal point associated with the angle. And so by definition, the sine of an angle is equal to 1 over the cosecant of an angle. Right? So this is really just restating definitions. We've got the quotient identities, again, a result of the definition of the tangent function. Tangent is defined as y divided by x. If we're talking about the unit circle, tangent is defined as the length of the opposite side divided by the length of the adjacent side if we're talking about right triangles. Either way, the tangent is equal to the sine of the angle divided by the cosine of the angle. Right? Then we've got the Pythagorean identities. Now, there are 3 of them here. We got sine squared plus cosine squared is equal to 1. Also, one step away from the definition, right? We first defined our trig functions on the unit circle. Unit circle is a circle of radius 1. Definition of a circle of radius 1 is the set of all solutions to the equation x squared plus y squared is equal to 1. So there's the definition of our circle. And then we take the definition of the sine function, the definition of the cosine function. Sine is y, cosine is x. So replace the x with cosine, replace the y with sine. And you get sine squared plus cosine squared is equal to 1. All right, so again, it's really a direct one step away from a definition. Now, this is 3 of the 9, I'll say 9 in total, variations of the Pythagorean identities, right? It's really just one equation or one identity written 9 different ways, right? So everything comes from this one. Everything comes from this guy. Sine squared plus cosine squared is equal to 1. So I'll write that over here. Sine squared plus cosine squared x is equal to 1. I'm actually going to write it twice. Sine squared plus cosine squared is equal to 1. Now, this is an equation. Like any algebraic equation, you can make any changes you want as long as you do the same thing to both sides. If we subtract cosine squared from both sides, right, they cancel. And we get sine squared x is equal to 1 minus cosine squared x. So if this is one version, let me use a different color highlighter. Too much green is no good. There's one version of the Pythagorean identity for sine and cosine. Here's another sort of related way of expressing it. Instead of having the 1 by itself, we could isolate the sine squared, have the sine squared by itself. Sine squared is equal to 1 minus cosine squared. Or we could subtract sine squared from both sides. So that will give us cosine squared of x is equal to 1 minus sine squared of x. We could do the same thing with the second and the third Pythagorean identities. We have one for sine and cosine, one for tangent and secant, one for cotangent and cosecant. Each one of those can be rewritten 3 ways. All right, so keep in mind, depending on what we're working with, depending on the specifics of the problem, we may want to work with one form or another form. And we'll see that throughout this video today. Then we've got the even and odd identities. These also are a result of the definitions, right? Early on in this video series, if you're going by chapters and sections, it would be back in chapter 1. I think the last section of chapter 1, maybe 1.8. No, actually, even before that, I think it's the beginning of chapter 1, 1.2. We talked about the definition of an even and an odd function. For example, we said, well, an odd function, by definition, is when f of negative x is equal to negative f of x for all values of x in the domain of the function. And then back we talked about the sine function, then we talked about the graph of the sine function, and we saw based on the graph of the sine function, it looked like it was symmetric to the origin, which meant the function was odd. And so once we know sine is an odd function, well, f of negative x, that would be sine of negative x, is equal to negative f of x, negative sine of x. Right, so that's this first one. Right? So these are all the definitions, right? Odd, sine is odd. Cosecant is odd. Tangent and cotangent, both odd. Right? Cosine, even function. Secant, even function. So these are sort of specific examples of our definitions of even and odd. Okay, so these are our fundamental trigonometric identities that we have so far. We're gonna add some more to this list. But anytime you have some equations or some formulas or some relationships or identities, whatever word you want to use, and they have a title or a name, right? Like these guys right here are called something. They are called the reciprocal identities. That's because they're important. These guys right here are called the quotient identities. These are the Pythagorean identities. Like these have titles, these have names. It's because they're important. There's a million other trig relationships that we could come up with. Not all of them are important. Not all of them have any significance. So we go on to the next slide. Here's 5 more trigonometric identities. These are 5 statements that are always true. They don't have a name like Pythagorean identities or reciprocal identities. They don't have a name because they're not significant in any way. But if we look at this first one, it's saying that if for any angle, you take the tangent of the angle, and then you take the cosecant of that same angle, and then you take the cosine of that same angle, and you multiply those all together, you will get 1. And that is always true. Okay, so what? Well, so nothing. There's nothing important about this first equation. We're just using it as an example. So this is an example of a trigonometric identity, an equation that's always true. Now, what we want to do is no longer take it for granted when I say it is always true. I say it's true. You say, okay, prove it. Why is it always true? So we're going to treat these 5 equal signs like they are question marks. Question mark, question mark, another question mark, and guess what? One more question mark. All right, we need to show that they're true. And that's the focus of this whole section is just this one question, one problem type, verifying an identity. I say this is an equation that's always true. Your job is to prove it. Every equation has 2 sides. There's a left side. There's a right side. They're connected with an equal sign. Right? Expression on the left, expression on the right. When you connect 2 expressions with an equal sign, you get an equation. There are 2 ways two general ways to verify that an equation is true. When an equation is always true for every value of x or t or theta or whatever variable you're using, when an equation is always true, we call it an identity. Two ways to show an identity is true. 9 times out of 10, I use method 1. Start with one side and change it into the other side. Generally, it makes sense to start with the more complicated side and simplify rather than start with the simpler side and complicate it, right? So method 1 looks like this. You've got the complicated side of the equation. And then you've got the simpler side of the equation. And you want to show those two are equal. So what you could do is take some things that you already know. Well, what do we already know? We know this stuff. We know this stuff. We also know how to do things like factor and multiply and combine fractions with common denominators and divide fractions. We like all the stuff we've been doing in our various explorations into solving equations, right? So we know how to work with equations, and we've got these so far we've got this pretty hefty list of fundamental identities. So assume all of these are already true. We don't need to prove them because they are basically definitions. Okay, so we could show that the complicated side is equal to this, which is in turn equal to this, which is in turn equal to this thing over here, which is in turn equal to that, which is in turn equal to the simpler side. So we're basically connecting the two at this chain of connections, these logical connections. It's not always going to be 4 steps. Sometimes it's 2 steps. Sometimes it's 8 steps. Sometimes it's 12 steps. These problems can get a little complicated. All right, but we start with one side and we manipulate until we get the other side. So method 1, you do this. Right? Method 2, sometimes this works better when both sides look complicated. So you've got the left side and you've got the right side. And so you start simplifying the left side. Left side's equal to this, which is in turn equal to this, which is in turn equal to this. And then do the same thing to the right. The right side is equal to this, so we're getting simpler. It's equal to something else, which is equal to something else. And then both of these guys are equal to something in the middle. So method 2 is to do something like this. Simplify both sides to get to a common place. You're basically connecting the chain from left to right. Right, but we're gonna focus mainly on method 1. It's the one I use almost always. When I say almost always, I mean at this level. This is like level 1, our introduction to verifying trigonometric identities. We're going to keep doing this. Section 5.2, more of these. Section 5.3, even more. Section 5.4, guess what? Some more. The further we go and the more identities we sort of amass on our list, the more complicated these problems may get. All right, so now back to that first problem. Well, how do we do this specifically? These are the two general approaches. You either turn one side into the other, or you turn both sides into the same thing, right? But now specifically, how do we go about that? Well, there is no step-by-step process I can tell you. There's no algorithm to follow. It's a bit more like solving a puzzle. You may try something and it doesn't work. You may try something else and that doesn't work. You may try a third thing and that does work. And that's why puzzles are fun. They're challenging. You pick up a puzzle, whether it's a Sudoku, a jigsaw puzzle, a word search, a little maze, whatever it is, a Rubik's Cube. You're not supposed to look at it for 2 seconds and then know exactly how to solve it. The fun in a puzzle is the process of trying to figure it out. And so we could talk about not, how to do it specifically, but some common approaches that you may want to try. Okay, so on the next slide, got some common methods. We've got our general approaches up top. You're going to do one of those two things. It's either change one side into the other or change both sides into the same thing. And then we've got some common methods for actually doing this. Okay. Method 1. When all else fails, or when you don't know what to do, a great thing to try is convert to sines and cosines. Right? Now look, these problems, they're going to be fundamentally different than most of what we've done so far. It is going to require starting a problem without having any idea how to finish it. Right? Starting a problem, having no idea how to even do the problem. You can't just stare at these problems. You have to try things. Right? Sometimes what you try doesn't work. You're trying to simplify. So if doing something makes the expression look simpler, you're probably on the right track. If doing something makes the expression look more complicated, you probably want to stop, go back to the beginning, try something different. Converting to sines and cosines. It's a common thing that tends to work relatively often with these types of problems. Factoring. Right? We talked about many types of factoring in previous videos. Difference of squares, pulling out a common factor, quadratic factoring. There's the reverse of that, multiplying, distributing, foiling, all the stuff that comes into that, umbrella term of factoring. Apply a Pythagorean identity. Well, I'm gonna go ahead and cross off the word Pythagorean. We don't have too many identities to choose from right now, but let's just say apply an identity. Pythagorean, I don't want to cross it off because then it makes it seem like you shouldn't do Pythagoreans. Apply a Pythagorean or other identity. Right? So far, we've talked about the even odd identities, the Pythagorean identities, the reciprocal identities, the quotient identities. Try applying one or more of those. Work with fractions, right? There's a lot of fractions in trig because 4 of the 6 trig functions are fractions, are defined as being a quotient. Secant is the fraction 1 over cosine. Cosecant is the fraction 1 over sine. Tangent is the fraction sine over cosine. Cotangent is the fraction cosine over sine. So there's a lot of working with fractions. Combine fractions, common denominators, split up fractions. Right? Another common approach, I didn't put it on here, but sometimes you're going to do something, and you'll see this at least once, maybe more, in this video, using the fact that x squared is equal to x times x. X squared is equal to x times x. For example, you may want to take sine squared and rewrite it as the sine of x times the sine of x. Sometimes that becomes helpful. Maybe it will in one of these 5 problems. We will see. So let's look at the first one. We're starting off with an easy one relative to all the other problems in this type. Verify identities. This one's pretty straightforward. So we're going to treat this like a question mark. We're going to start with one side of the equation. We want to take the tangent of x times the cosecant of x times the cosine of x and show that it's equal to 1. Right? Assume these are all true, right? Our goal is not to determine if they're true or false, or if they work always or sometimes. Assume these are identities. These are always true. Our goal here is to prove that. All right, well, method 4 doesn't seem to play yet. There's no fractions, so we can't combine or separate fractions. Pythagorean identity, it doesn't seem like that plays. There are no squares, so there's no sine squared, cosine squared, tangent squared, so on. Factoring, well, it's already in factored form. Everything's multiplied together. So when all else fails, method 1 convert to sines and cosines. Well, tangent. And you know what? I'm going to work down. Tangent is equal to the sine of x over the cosine of x. Right? Quotient identity. Cosecant of x is equal to 1 over the sine of x. Reciprocal identity. And cosine, well, if the first two we're treating like fractions, let's treat this like a fraction as well. Cosine is cosine over 1. That's not an identity, that's just a fundamental property of the real numbers. Any number divided by itself is equal to 1. Right? So I'm going back to this slide. Let me erase all this nonsense that's on here. Right? So in this problem, we use the fact that the tangent trying to stay on this. Trying to stay on this one slide. I'm sorry about this. We use the quotient identity. In this first part. We use the reciprocal identity on the second part. Right? So now, if we multiply across, we get sine x times cosine x on top. We've got another sine x and a cosine x on the bottom. Anything divided by itself is equal to 1. So sine x over sine x is 1. Cosine x over cosine x is also equal to 1. So this expression is equal to 1. And that is that. All right, we started with the left side. This was just a couple of steps. We end up with the right side. This was just the first problem. They get a little bit more interesting. All right, so look at this guy. Secant x minus secant x times sine squared of x is equal to cosine of x. All right, so for any angle, if you take the secant and then you subtract from that secant times the square of the sine, you always get the cosine of the angle. So I'm going to start with the left side because it looks more complicated than the right. And now what can we do? There are a dozen different ways we could go about this. Right? These are not problems where like you need to ask yourself, what do I have to do? Just do something. That's the important thing. Just try something. Right? Try converting everything to sine and cosine. Maybe that works, maybe it doesn't. Try factoring. There's a sine squared here, so maybe try applying a Pythagorean identity. It looks like the only method that we can't try is method 4 because there's no fractions yet. Now we could rewrite secant as 1 over cosine and then start combining fractions, but in this first step, there's no fractions yet. So you might want to pause the video for a few minutes and try to work this one out. I'm actually going to start by factoring. I don't know if it's the simplest way, but to me, this is where my mind goes. And when I give this problem on an exam, 10 students can give me 10 different step-by-step processes, and all 10 of them could be 100% correct, right? The only criteria here is that you connect the left side to the right side. It doesn't matter how you do it, as long as every step along the way, every change, every manipulation you make, you're not breaking a rule. If I do it in 5 steps and you do it in 7 steps, we're both 100% right. So I'm going to try factoring first. So I see a common factor. There's a secant in the first term. There's a secant in the second term. So I would factor this in the same way I would factor the expression x minus xy squared. You see there's an x in both terms, so I could factor out an x, and I'm left with 1 minus y squared. Okay, so factoring the same way, factor out secant x. And from that first term, we're left with a 1 minus. And from the second term, we factor out the secant. We're left with a sine squared. Now, this is one of those situations where we have a anytime you see sine squared, anytime you see any of the 6 trig functions squared, think Pythagorean identity. It doesn't mean you're definitely going to use it, but you want to consider it and think maybe this is a situation where I might want to. Sine squared x plus cosine squared x is equal to 1. And I talked a little bit earlier about how we could reshuffle this equation, shuffle around the terms. And if we get cosine by itself, then cosine squared of x is equal to 1 minus sine squared of x. Okay. So we can replace secant of x. We keep the secant of x. We replace the sine, the 1 minus sine squared with the cosine squared. So that is a Pythagorean identity. Okay, we're getting close. The secant, this is one of our reciprocal identities. Secant of x is 1 over the cosine of x. Now, if we multiply, it looks like we have cosine squared of x on top, and we've got cosine of x on the bottom. Remember a little bit earlier when I said sometimes you might want to do this. X squared is equal to x times x. Well, cosine squared is cosine of x times cosine of x, and then you've got a cosine of x on the bottom. Common factor, top and bottom. Cosine over cosine is 1. And we are left with the cosine of x. And that does it. We have verified. All right, so this whole process is your answer, right? Everything here is like what you're looking for is this step-by-step connection that links one side of the equation with the other side, right? So the answer is not cosine of x. We don't circle this and say, okay, there we're done. There's the answer. The answer is everything, all of it. How we get from start to finish is the proof. All right, let's do another one. Verify the identity sine of t times the tangent of t is equal to 1 minus cosine squared of t divided by cosine of t. Now you pick one side you might think is more complicated. So maybe we'll start with the right side. So let's start with 1 minus cosine squared of t divided by the cosine of t. And we want to, again, we want to do this is equal to something, which is equal to something, which is equal to something, which is equal to sine of t times the tangent of t. I want to connect the dots. Well, the first thing I see is that's looking just like a Pythagorean identity situation. So let's bring that guy back into the mix. Sine squared of t. Now the variable could be whatever you're using. If it's an x or a t or a theta or an alpha, that's your variable. So sine squared of t plus cosine squared of t is equal to 1. If we subtract cosine squared from both sides, we get sine squared of t is equal to 1 minus cosine squared of t. All right, so 1 minus cosine squared is equal to sine squared. Now let's do that trick again where we take the sine squared and split it up as sine of t times another sine of t divide that by cosine t. Now, the reason in this case we want to split it up is because, well, what is sine over cosine? Well, that's tangent. Circled one too many t there. That's tangent. So it looks like we're about done. So we could split this fraction up into two fractions. So this is sine of t over 1 times sine of t over cosine of t. We got two sines on top. We got a single cosine on the bottom. That looks good. Sine of t over 1 is the sine of t. The sine over the cosine, that's the tangent. So that's tangent of t. And that is exactly what we're looking for. Please don't look at this as the solution. This is a solution. One of many. You could have started with the left side and turned it into the right. You could have started off by factoring. So let me use a different color here. You could have said 1 minus cosine squared of t divided by cosine of t, and said, okay, well, the top of that fraction looks like a difference of squares. So that factors to 1 minus cosine of t times 1 plus cosine of t divided by cosine of t. I don't know if this would, this is not going to be an easier approach, but just try something. You try something, it looks like it's getting more complicated. So you say, okay, stop. Let me go back. I'll try something else. Instead of factoring, let me try a Pythagorean identity. You could have started with the left-hand side and converted everything to sines and cosines. There are always multiple ways to verify an identity. What you care about is that you start with one side, you end up with the other side. In this case, there were 3 steps in between. This is equal to that, that's equal to this, that's equal to this, and that's equal to this. It doesn't matter how many steps it takes, as long as you connect the left to the right. All right, let's do a couple more. I don't think there's any discussion here necessary in terms of which is the more complicated side. I think we'll start with the left, turn it into the right. So we've got 1 minus sine squared of x over 1 plus the cosine of x. I'm going to write a little bit smaller just to make sure we have enough room here. See, 1 minus sine squared of x divided by 1 plus cosine of x. Okay, well, let's see. What can we do? I'm going to try combining 2 fractions into 1. I'm going to try combining 2 fractions. I don't think we've done that one yet. So to get a common denominator, we could take that first, this number 1 right here, and write that as, well, let's show all the work, actually. Right, so I took 1 and wrote it as 1 plus cosine x over 1 plus cosine of x, so we get a common denominator. You could write the number 1 as anything over itself, except 0 over 0. Right, so now we've got this common denominator. So we could put those two fractions together. We got 1 plus cosine x on the bottom. On the top, we've got a 1 plus cosine x minus sine squared of x. All right, so all I've done so far is taken these two terms and combine them into one single term by getting, or one single fraction by getting a common denominator and subtracting. Is this the simplest way to solve the problem? I don't know. It makes sense to me. All right, so now it looks like there's a couple of cosines and there's one sine, right? So let's see if we could turn that sine squared into a cosine squared. Well, we could definitely do that. We've seen this already. Sine squared is equal to 1 minus cosine squared. We also have the cosine squared is equal to 1 minus the sine squared. So which one are we going to use? Well, let's see. We've got a 1 and we've got a minus sine squared. So if you have a 1 and a minus sine squared, you could turn that into a cosine squared. So we've got cosine of x plus cosine squared of x divided by 1 plus cosine of x. And let me just sort of try to color code things. We use this equation up here. All right, so everything in green is that step. We took those two, and based on that formula, replace the 1 and the minus sine squared with a cosine squared. All right, this is looking good. I think we're close. I think we are a couple steps away. So we combined fractions. We applied a Pythagorean identity. Now I think it's time to factor. So method 4, then method 3, then method 2. Looking at the numerator, I see some like terms there. We have a cosine in each term. So if we factor out a cosine of x, we did this in the second problem. We factored out, I think it was a secant of x. Let me just go back a couple of slides. Yeah, this first step here, we factored out a secant of x. So we're doing the same thing. And that's the thing with these problems. You got to do enough of them till you start seeing common things that tend to work over and over. All right, so if we factor out a cosine of x, again, I'm looking just so we know what we're focusing on right now. Let me erase all of this green highlight. Right now we're looking at this, and we want to factor. In this case, we have a greatest common, or we have a common factor we could pull out. We could pull out a cosine of x. So we're left with 1 plus cosine of x. So this yellow part became this yellow part. Cosine x plus cosine squared of x. And this is the same type of factoring we've been doing many times over many of these videos. So how would you factor x plus x squared? Well, there's a common x. You would say, okay, well, factor out an x. We're left with a 1 plus x. It's the reverse of the distributive rule. It's exactly what we did here. Instead of using an x as a cosine of x, but we have two terms, a common factor, pull out the common factor, and we reverse the distributive rule. Well, this looks good because now we've got a 1 plus cosine in parentheses on top. We've got a 1 plus cosine on the bottom. So I think this next step, do a little algebraic canceling. 1 plus cosine over 1 plus cosine is equal to 1. And that leaves us with the cosine of x. And that completes the proof. So this, again, this is all answer right there. It's not the only way. I mean, you might want to pause the video here and see if you could redo this problem a different way. Let me get you started. You could do 1 minus sine squared of x divided by 1 plus cosine of x. That's just I just copied the left side. That's where we start. And then we could say sine squared is 1 minus cosine squared. Right, so we could take the sine squared of x, replace it with a 1 minus cosine squared of x, because that is this version of the Pythagorean identity. So we could start this problem by doing this. A completely different approach. But I'll tell you right now, this will work. This will get you, in another 4 steps, 3 or 4 steps, it'll get you to cosine of x. All right, what would you do next? Well, we could factor that. That's a difference of squares. Right? We know a squared minus b squared is equal to a minus b times a plus b. So if we apply this formula to that, right? So you may want to see if you're able to take that, what I have there in black, apply that difference of squares formula, see if you could get cosine of x. It should just be a few steps. Shouldn't be much longer or longer at all than the way I did it. All right, but the thing to keep in mind is, one, there are many ways, and this is just two of a number of different ways I could see us getting through this problem. There are a multitude of different ways to verify the identities. And two, it's perfectly fine to have no idea how to solve the problem. You just have to try things. So these method 1, 2, 3, and 4, these are not everything. This is not an exhaustive list, but these are 4 common things that tend to work often. So just try one. If it doesn't work, try something different. Right? You see a sine squared, try Pythagorean identity. You see cosecants and cotangents and tangents, try converting to sines and cosines. See if that helps. It might not. All right, I think there might be one more. Yeah. We got cosecant squared theta divided by cotangent theta is equal to cosecant times secant. I'm going to start with the left. Let's say, I think the left looks a little more complicated than the right. So cosecant squared divided by cotangent. I know what I'm going to do first. Let me pause the video for a moment or 3. Just think about what you would do first, and then maybe it's going to be the same thing I would do, maybe something different. Well, it looks like there's, with these 4 methods up here, there's only 2 that apply, right? For our first step, there aren't multiple fractions. And I don't think splitting this up into 2 or more fractions is going to help, right? There's really nothing to factor. We've got a cosecant and a cotangent, so we could convert to sines and cosines. And there's a square there. There's a cosecant squared, so we could also apply a Pythagorean identity. Try one of them. If you said start by applying a Pythagorean identity, you're not wrong. It's just not what I did. I don't know which method is going to be more succinct or more shorter, but we haven't done that much of converting to sines and cosines. So I'm going to start off by converting everything to sine and cosine. So rather than go back to the original, like to the slide with all of the identities, you want to have all that stuff out. I mean, actually, I will go back. Like, unless you have this stuff memorized, maybe you do. We've used all of them quite a bit up until this point in the previous discussions, previous videos. But unless you have everything on this slide memorized, you probably want to have this out somewhere, written down, printed up next to you while you're working on these types of problems. Okay, so cosecant, according to the reciprocal identity, the cosecant of theta is equal to 1 over the sine of theta. And the cotangent of theta is equal to the cosine over the sine. Cosine of theta over the sine of theta. And so the first one is one of the reciprocal identities. The second one is one of the quotient identities. They both apply here. So if cosecant is 1 over sine, then cosecant squared is 1 over sine squared. We've got cotangent on the bottom. Cotangent becomes cosine over sine. All right, we've got a compound fraction, but that's not a big deal. We know how to deal with that. Keep, change, flip. So we take the fraction on top. multiply it by the reciprocal, the fraction on bottom, keep, change, flip. Okay. Now we got 1 over sine squared times sine over cosine. Now, let's see. So on top, if we multiply these two fractions and combine them into one, we've got a sine theta on top. We got two sines and a cosine. So I'm going to, again, do that little trick, split up the sine squared into sine theta times sine theta. Then there's a cosine theta. All right. Top times top, 1 times sine theta. Bottom times bottom, sine squared times cosine. So that's sine times cosine. Cancel the common factor, top and bottom. So there's a sine theta on top, a sine theta on the bottom. So now we're left with 1 over sine theta times the cosine of theta. Now it looks like it may be beneficial to do this. Separate one fraction into two. So we could take the 1 over sine theta cosine theta, and we could rewrite that as 1 over sine theta times 1 over cosine theta. And now I think we're there. Now let me see. There's a little bit of room down here. 1 over sine theta is equal to the cosecant of theta this is equal to that, and 1 over the cosine of theta is equal to exactly what we need, the secant of theta. And that does it. That's what we're looking for. Even though we're not working with the right-hand side, don't forget it's there. Don't forget where you're trying to end up. And so that completes the verification or the proof that this is indeed an identity. Right? We said the left-hand side of the original equation, right, is equal to this, which is in turn equal to this, which is then in turn equal to this, which is then equal to this, which is then equal to this, which is finally equal to this. Right, so 1, 2, 3, 4, 5, 6 steps. Not terrible. But you can see, like, the progression from the first problem to the fifth problem, they're getting a little bit more difficult. And they, it only gets more interesting from here. It's a complicated topic, right? This is not something you do definitely not a type of problem where you watch me do 5 problems and that's it, and then you should start feeling comfortable about them. You should be more confused now than you were at the beginning of this video, right? You got to do more. You got to do more of these problems. You have to see the patterns. Mathematics is the science of patterns. The more problems you do, or redo, or watch being done, the more problems you work through, the more you see these common occurrences, these things that happen over and over. Right? This little trick right here, I think it happened 3 times. Where we took sine squared and wrote it as sine times sine, or cosine squared and wrote it as cosine times cosine, or secant squared, wrote it as secant times secant, right? It happened 3 times in only 5 problems. So, you start seeing repetition. You start seeing things work, the same thing work multiple times. So then you sort of have this database in your mind of things that have worked before, things that have commonly worked before, and you just try those things, right? Verifying trigonometric identities involves trial and error. Has to. Sometimes the first thing you try is perfectly fine and it'll get you through. Sometimes the first thing you try leads you to a dead end. Not a big deal. You start over, try something different. All right, that is it for this video. In the next sections to come, 5.2, what we're going to do is add some more identities to our list. Important ones. So if I go back to this slide, we're going to add another box with maybe 6 more identities in the next section. Then we're going to add 3 more boxes with about 12 more identities in the section after that. We're going to just keep adding to this list. So the more identities we have to choose from, the more complicated it is to verify identities because we just have more options. All right, more on this later. That's it for 5.1. I hope this was helpful.